Okay, let's get real. Okay? No, real. We've been living in this ideal world for 2 whole chapters. You may not have noticed it was 2 whole chapters, but we have been just living in la la land, pretending the world was perfect. Today we're going to deal with what's the real world like. Okay? And what I need you to get out of this is, well, you're going to be able to calculate it. Okay? We're going to do that. But as we get there, we're going to talk about why it's not working, when it does work, when we can trust our answers, and what that math is telling us. How does it correct for the things that are wrong? Okay? So, ideal gases don't exist. There's no such thing as an ideal gas. I think I've said that a few times. We were lying to ourselves this whole unit so far. So how are real gases different than ideal gases? Well, molecules really take up space because they're matter, and one of the things that makes them matter is they have volume. And the math for, what it is the math for an ideal gas assumes it can be anywhere in the container. But in truth, it can't be anywhere in the container because it can't be where there's another molecule. Right? I can't put 2 bowling balls in the same spot. Okay. Normally we ignore that because the molecules are so far apart, but we know it's not true. Molecules really do take up some space. Okay? And there are attractive forces, because that was the answer to one of our homework questions yesterday. How do we know that there are attractive forces between molecules? How are we sure that molecules stick to each other? What do we see that tells us that molecules stick to each other? Anything that's not a gas. Because there'd be no liquids or solids if they didn't stick to each other. So the fact that you see a solid means the molecules stick to each other. The fact that you see a liquid, why is that liquid there? Because the molecules are sticking to each other. So that means that we're pretending that they bounce off perfectly, but they actually stick a little bit. Right? So when does it work? Okay? What conditions make it work? When do real gases behave like ideal gases? Well, one of the places when the molecules are far apart. This is not two different sets of molecules. This is the same set of molecule in 2 different boxes. Got a bigger box here. So it changes from here to here is the box size. All in a little box, open up and put it in a bigger box. When those molecules are further apart, they take up a smaller percentage of the space. It's the same number of molecules in both boxes, but it makes much more sense to ignore it here than there. Okay. So if they're far apart, ignoring their volume is reasonable. We know it's not right. So what can we measure that will tell us that the molecules are far apart? Well, if they're far apart, they're not going to hit the walls very often. So that's going to be at a low pressure. The lower the pressure, the better we can expect our gas laws to work. Because at low pressure, they're going to look like this in the box. High pressures are going to look like that. Well, maybe not that extreme, but they're going to take up a bigger percentage of space. Okay? So that's how we deal with the fact that they take up space. We say we're only going to measure them if the pressure is low. We're only going to trust our numbers if the pressures are low. Okay. Real gases behave like ideal gases when the molecules are moving fast. Why would that matter? Well, if you're moving fast, you're not next to each other for very long. You bounce off and you leave. And if you're not next to each other, you can't stick to each other. So the attractive forces don't really play a role. So if I got them moving fast, they're not going to get an opportunity to stick to each other. And what would I measure that tells me that they were moving fast? Temperature, well, it would be at a high temperature. And what we mean by a high temperature is a long ways above the boiling point. So nitrogen has a boiling point of about 80 K. 77 K, 80 K. Okay? We are a lot warmer than 80 K. We can expect nitrogen to work in here. Okay? Water has a boiling point of 100 degrees Celsius. We're actually below the boiling point. We would expect those molecules to stick to each other fairly well here. So in this room, I'd trust the numbers for water a lot less than I trust the numbers for nitrogen, because we're closer to that water's boiling point. Make sense? Okay, so we mean high temperature means far above the boiling point. And now I'm going to show you a couple of graphs, and it's a matter of what these graphs can tell us. Okay? So both graphs are graphing the same function. Okay? And what they're graphing is the PV over RT. Well, PV over RT for 1 mole of gas will be 1. Does that make sense? Because N equals PV over RT. So as you raise the pressure, notice what happens. First, they drop down below 1. An ideal gas would be 1 all the way across. That whole thing all the way across would be 1. So first thing is, I end up with my numbers that are too low. I would report it as less than 1 mole. Why? Well, because the pressure's too low, because intermolecular forces are playing a role. They're sticking. Okay? And notice the numbers on atmospheres: 200, 400, 600, 1,000. We're talking really high pressures. So we spend our time over here, so we can trust them pretty good. But when you get the pressures really big, the intermolecular forces play a bigger and bigger role, and if they're sticking to each other, they can't bounce off and hit the wall. So the pressure gauge is going to be wrong. Your pressure gauge is going to be too low. It's going to be lower than the 1 because the molecules are sticking to each other. Okay? But then I get a different variation because when I get to really high pressures, I have pushed those molecules close together. So they're taking up a big percentage of the space. So my volume available is really less than the volume they put there. Okay? So they can't move as far, so they're going to hit each other. You're going to hit the walls more often because they're hitting each other more often because they're taking up more of the space. So when the pressure's low, really low, near 1, we can trust it. Anywhere after that, we don't trust. Now notice the different gases. Notice that it works so much better for nitrogen, especially down low, than for CO2. Well, that's because nitrogen and CO2 are both nonpolar, but carbon dioxide's a lot bigger than nitrogen. It's a longer line. Okay. CH4 is nonpolar, so N2 is also nonpolar, so CH4 is middle-sized, so that's why it's in the middle of the graph. It's the middle-sized piece. Notice H2 goes like that, because it doesn't stick together at all. It doesn't have, it has the weakest of the intermolecular forces, so they never really play a role down here. Because we get above hydrogen's boiling point really quickly, because hydrogen boils at 20 K. Now, this is the same graph, except here they've done the same temperature, or same gas, at 3 different temperatures. Okay. When can we trust it? We can trust it right here, which is low pressure. Okay. We trust it closest there, so lowest pressure near 1. And notice what the temperature difference is. Which one of the temperatures can I trust best? Which one stays close to that line? 1,000 Kelvin. Okay. At 200 Kelvin, my numbers get off significantly when I get up to 600 atmospheres. By the way, you don't want to be around 600 atmospheres. Bad things happen. Okay? Does that make sense? When to trust it. So let's see. When would you trust it? Can you see this is really just two true-false questions tied to each other? Okay. Could I trust myself better at 2 atmospheres or at 1 atmosphere? Well, do the gas laws work better at low pressure or high pressure? They work better at low pressure, so it's one of these two. Right? Does it work better at high temperature or low temperature? High temperatures, got to be B. Okay, so what do you do if you don't want to pretend? Well, then you use van der Waals equation. Van der Waals was that Dutch scientist who studied the weak attractive forces between molecules. We have an equation to do when it's a real gas. We've just been ignoring it. Here's why. There's the equation. You don't have to memorize this one. This one will be provided for you, but you have to be able to use it and interpret it. Okay, so POBS, that means the observed pressure, the thing your gauge is going to give you. Observed. My pen just doesn't want to write today. So that means observed. That means if you measure the pressure, that's what you're going to get. And we said the pressure we're going to get was going to be too low. So I'm going to take that pressure I get, I'm going to have to add something to it, because the molecules were sticking to each other. So A is a number that depends on how much the molecules stick to each other. And you look it up. You just look A up. Now, I talk about this. This is how many moles there are in a given volume. That's how concentrated the molecules are. Because the closer they are to each other, the more they're going to stick to each other. And since they're going to stick to each other, I'm reducing the pressure this way and I'm reducing the pressure that way, so I have to square the effect. So pressure I get is too low, but I can correct that by adding a number about how sticky it is times how concentrated they are, how close together they are. And I need to square that. And that would mean that they're not hitting the wall, so I'm correcting for them not hitting the wall hard enough. Okay? Then I have to correct the volume, and I got to correct the volume because the molecules really take up space. So B, I got to subtract for the space they take up. So B is about how big they are, and I got to multiply it by how many I have. The more I have times how big they are, that will tell me how much of the space they're taking up. So there's tables in the back of your book for these gases that have the van der Waals constants for a bunch of different gases. Homework tonight, I'll print them for you. Okay. So there's the equation. So, number 21. Number 21. Calculate the pressure of 1 mole of CCl4 at 273.15 degree 1 Kelvin and 24.2 liters with and without the assumptions. So we're going to use the ideal gas law first to find the volume, or to find the pressure. Then we're going to use the real gas law to see how it's different if you use the real gas law. Does that make sense? So let's give this a try and see if you can see what the heck I'm doing behind my back. Okay. Pen. It's right here. Okay, so the first one, following the ideal gas law, that's going to be pretty straightforward, right? Yeah. Nope. Oh, this will be online. And here's the paperwork. Okay. So, let's give this a go. Center it. All right, so ideal gas, P equals nRT over V. Right? So, I got 1.000 moles times R, and I want the R in, it doesn't matter what unit I pick R in. Okay? 0.082, and since these got 4 sig figs, I'm actually going to add another sig fig. I don't want my R. I don't want to round off R to limit my sig figs. I looked it up. They know it's like 7. So that's liter atmosphere over mole in Kelvin. So that's the 0.0821 with 1 more sig fig is 0.08206, and the temperature was 273.15 Kelvin divided by the volume, 22.42 liters. See this. So, I'm not pushing the 1, but 0.08206 times 273.15 divided by 22.42 equals 0.9998 atmospheres, which is really 1 atmosphere, which is not a big surprise. Are we okay? It should be 1, because 1 mole should be 22.42 liters at 0 degrees Celsius if the pressure is 1 atmosphere. Okay, so quick and easy. Now we got to try the nastier one. Okay. So, P, that's what I'm trying to find. Plus A. So I went up in the book, looked at the back of the book, looked up A for CCl4, and I got 20.4. And the units are atoms liters squared over moles squared. Times N. Well, they said it was 1.00 moles. Over V, 22.42 liters. That whole quantity squared. Times V minus 1. V was 22.42 liters. Minus N, 1.000 moles, times B, I ran out of room here. B is, for CCl4, it is 0.138 liters per mole. And all of that equals 1.00 moles times R and times 273. It's a long problem. If you tried to push this into your calculator all at once, you would hurt yourself. And you'd lose sig figs, because we got both adding and multiplying. So I'm looking at these brackets. First, I'm going to have to multiply, right? So I multiply those numbers. 20.4 divided by 22.42 squared. I'm not pushing ones. Equals, now I'm at P plus 0.0406. What units? Well, I got liters squared, and this is liters on the bottom and it's squared, so liters squared cancels out. I got mole squared on the bottom. That means I got mole on the top, but it's squared, so I got mole squared cancels out. And I'm left with atmospheres, which is really good because I'm going to try to add a pressure to something. I want to add that pressure to atmospheres. And that 0.0406 has 3 sig figs like the 20.4. Okay. Times, well, I can actually, so I got 22.42 liters minus 0.138 moles cancel out. I'm left with liters. And that still equals 1 mole times R times T. Right? So that means P plus 0.0406 atmospheres equals 22.28 times 22.28 liters equals 1.00 moles times R times 273.15. Okay. So the first thing I have to do is divide both sides by the 22.28 liters. So now I get P plus 0.0406 atmospheres equals 1.000 moles. Now I want the R in atmospheres because that one was in atmospheres. So 0.08206 liter atmosphere over mole Kelvin times 273 K divided by 22.28 liters. So that's 1 times 0.08206 times 273.15 divided by 22.28 equals 1.006 what units? Well, liters cancel, Kelvin cancels, mole cancels, and I'm left with just atmospheres. So minus 0.0406. So P equals 0.9654. Because there's 4, oh, actually, you only got 3 decimal places, so 0.965 atmospheres. Okay? So it's a tedious. Any really hard steps there? It's all just PEMDAS, isn't it? And keep a track of sig figs and units. It's a pain. We had to do all that work to get 0.965, whereas in one step, I get 0.998. Are those things hugely different from each other? No. So when we started this, I said, we use the ideal gas law because it works pretty well and it saves us a lot of time. Does that make sense? You see, now you see it works pretty well most of the time, and it does save us a lot of time. Because you got to admit, that first question was a lot easier to answer than the second one. Okay? Yep. Questions? You just need to practice playing with those numbers, so that's why I'll give you some practice. So, okay, so again, you can't just push it in your calculator, you lose track of sig figs along the way. Because you got adding, subtracting, and then you got more subtract, then you got multiplying, then you got adding, subtracting again. So now we're just going to solve these for pressure. You could solve them for all the pieces, but imagine what solving for V would be like. Well, it'd be like what I solved for P. We solve for temperature. No, solve for moles. Yeah, solve that for N. Would you like to solve that for N? Not because it's got a squared, a 1, and a 1 on the other side, so got squared terms in there. It divides out eventually. Do not attempt to do this on this piece of paper. Okay, so on number 1, you're going to have two answers, one for the ideal gas law, one for the real gas law. And 2, same thing. And then I want you to look at those answers and see why it worked better for one of those two. And think about, not in terms of math why it worked, in terms of particles why it worked better. What is different about those two situations that would explain why it worked better? So it's going to, same thing for 4 and 5. 4 and 5 are going to be, figure out the same things and see which one worked better. Look at what changed and see how that would affect how well it worked. So I'm looking for a particle answer to 3 and 6. Does that make sense? Particle answer for 3 and 6. Technically, all the Y answers this unit should be about what little tiny particles are doing, because that's our theory. So first the ideal gas law, then with. So your homework should look a lot like, zoom out.